On exam 3, we had two broad sets of topics. We were looking at liquid, solids, and materials, and then also ideas involving thermodynamics, energy, heat work, and enthalpy. Looking at the different questions that were on the exam that you could choose from, for the first set, when looking at the viscosity of a liquid, I saw strong explanations involving temperature. The best responses also looked more deeply at the structure and considered how the structure could entangle molecules, and also how the structure could influence the intermolecular forces that were present. And those were supported by looking at specific molecules. The descriptions and explanations involving ionic liquids I thought were strong. The very best answers looked more closely at the properties and how those were related back to the structure. Liquid crystals, I don't think any student responded to this one, so no love for the liquid crystals. Turning to solids, I thought responses looking at the properties of, in this case, metals and network solids were well done throughout. As far as which would be most useful for classifying them, um, I liked reading your different arguments. There wasn't a single answer for that, but in general, I thought the responses were persuasive. Looking at the unit cells, only one or two students responded to this one. I think perhaps what might have made it more challenging, or why someone would look past it, was seeing how one would classify these as primitive face-centered or body-centered, because I think it was both looking at the provided unit cell and thinking back to the idea of what would be the motif that would be populating that. For calculations involving the percentage of empty space, very high success rate on that. Here was an example of the calculation. So I thought this was well done, and it was also helpful seeing the work. For the set of questions looking at different aspects of materials, comparing interstitial and substitutional alloys, really nice descriptions for the structure. And the very best responses also connected aspects of the structure to the properties. Comparisons of the sea of electron model with the molecular orbital. Good descriptions of both. I found it interesting on the analysis of strengths and weaknesses. Most of the strengths for the molecular orbital theory were discussed in terms of being able to explain differences in melting point. I find that interesting because, yes, that was the first comparison that we made that sort of pointed out a failing of the sea of electron model. Some students went on and discussed another strength, which I definitely view as a strength, which is how it can do a much better job explaining the electronic structure. The descriptions of the electronic structure, whether we're talking about insulators, metals, semiconductors, fewer students tackled this question, but I thought those that did a nice job. Within this one, we had, I think, two questions that really allowed students to demonstrate their understanding. The first one looking at our gas in a piston and including supporting calculations. The idea here, if you recall, within class, we saw that we could have irreversible expansion, where we removed our weight and the expansion was against 1 atmosphere. Or we could do it in 2 steps. And both of those steps would have a particular amount of work, and that we could be using PV equals nRT to figure out for a given pressure how the volume changed. So we could do a calculation where we're considering the amount of work in 1 step or in 2 steps, and contrasting that to a isothermal reversible expansion where we could have many, many, many infinitesimally small steps, which would lead to the maximum amount of work. The students that tackled this one, I thought, did a really nice job. It's not easy coming up with your own numbers for this. I know this is a question that would have a much higher success rate if values were given, but I thought it showed a really high level of understanding to be able to come up with suitable numbers for this. And suitable numbers are really closely linked to what would be the pressure and the corresponding volume expansion. Here's a case where we're seeing that when we have infinitesimally small steps, we see the greatest amount of work being done. and then pretty close values for the scenarios here for B and C. Another description of the same. So I thought this was a question that really, it's a challenging question. I thought it was well done for the students that tackled it. When looking at this description of internal energy and how it's related to heat and work, uh, one thing I noticed within this one, uh, many students initially define the internal energy as being the change that's involving heat and work, which I get. That's the very first sentence right there. So I completely understand that. This connection, though, at the particle level, in general, I found that the connections to the particle level, if students also defined internal energy as the sum of all the kinetic energy and potential energy, it seemed to set them up a little bit better to describe what was taking place at the particle level and distinctions between what work meant and what heat meant. Both of these questions really, I think, gave you an opportunity to display your understanding. There were a lot of ideas embedded within both of these. So first of all, looking at the calculation, the idea of, well, what would be a heat capacity term that I could use? Well, I'm going to look at the molecule and I'm going to consider translations and rotations that will give me a sense for what the heat capacity. In this question, it was stated that it was at constant volume. So being able to estimate that was the crucial first step. Being careful with the units of R, what I found there is within this question, you're using two different R values. One in liter atmospheres per mole K and one in joules per mole K, as the student is showing, to come up with what the final temperature would be. A couple variations that I saw within this one, it wasn't as clear where this estimated heat capacity was coming from. So they weren't necessarily doing an analysis based on the particle motion. So they might work it through, but it wasn't as clear where that feature was coming from. Another idea that I saw that I now recognize in hindsight, when we're looking at the equipartition of energy, as it's shown here in increments of 1/2 kT, if you recall, then on a molar amount, it would be in terms of R instead of K. But as I look back at these images, it sure looks like, okay, the heat capacity is involving kT. But you notice then when we're doing our bookkeeping afterwards, it's just in units of R, not RT. So I see this as, I understand why a couple students were putting those terms together. What they're trying to show here, what Atkins is trying to show here, is a way to think about the energy is with this value of kT or RT if we're thinking about molar amounts. But when we're then using it as an actual heat capacity term, it's just in terms of the amount of R, in terms of increments of R. So as I saw several students work through using that within their estimate, that sort of comes back to me as, okay, I didn't make that distinction clear enough. This particular question is another one where I don't think I made the distinction clear enough of what was going on. So within this one, this is how I see it. If I look at A right here, definitely a phase change. It's endothermic to go from a solid to a liquid. Heat's going in. The fact that the temperature is not changing is because the potential energy is changing. I'm changing the position of the molecules, the particles that were in a solid to a liquid, but I'm not raising the average translational kinetic energy. I'm not raising the temperature. That's what I view as taking place here. Now, crucially, I'd say the internal energy is changing. Heat is going into the system. I don't see any work being done. Heat is going into the system, so the internal energy is going up. The internal energy of the liquid is higher than the internal energy of the solid. This right here, I was seeing a lot of discussion that was saying, no, the internal energy should be zero. The change in internal energy should be zero. Therefore, any heat will be offset by work. That's not correct. If I look within the second case, I'm viewing this as a chemical reaction of a solid and a gas combining within the reaction to form a gas. I see this as an endothermic process. I'm looking at the thermometer for that. I found it interesting that many of the analyses here included the word sublimation. I don't necessarily think about it that way. I mean, I'm thinking about it as a chemical reaction, But in terms of the sublimation, I mean, in a sense, that's not wrong, right? If we think about what was taking place when we're combining our enthalpy of reaction with Hess's law, it doesn't have to be what's actually taking place as long as we go from our reactants to our products. So if within the process one is viewing, okay, sublimation is involved, it's not incorrect. I just found that interesting. My head didn't go there. I'm definitely seeing, though, expansion and PV work being done. Coming back to this idea here of the internal energy increasing versus the internal energy remaining zero, I find myself wondering, is the view that the change in internal energy was zero connected somehow conceptually within the class to our description of this isothermal expansion of an ideal gas in a piston? That was a case where it was isothermal and the change in internal energy was zero. I'm just speculating there. I'd be curious on your feedback, whether you are seeing the internal energy remaining zero for a phase change because of this isothermal characteristic. We had two examples here of what I would think would be calculations for both. So within this first case here, oops, sorry about that, we have this description of we're combining a cold piece of metal, we're combining it with water, and we're going to be freezing the water. And we've got different values that we could choose from. When I was looking within the shown work here within the calculations, a key step I found was this one right here. This idea of what is the initial temperature for our piece of metal? And the piece of metal is going to go to the freezing point of the water. So we can use that information. We need to use that information to consider the temperature change for the copper metal. I found really what would the final temperature be an important step within here. And if we're freezing the water, okay, we can say, well, what would be the freezing point for that? Okay, I know that will also be the end point for the piece of metal. The idea that the heat exchange was going to be equal between the water and the copper, just a change in sign. Most students had that point, but then sort of connecting it to what the final temperature would be, I found is an important part of it. This next question right here I found was really interesting. I viewed this one as one where an initial calculation would help. And by that I mean we're taking a comparison involving water vapor and copper metal. The values that I see for the specific heat are per gram. If I want to compare these particles with particles, I need to scale it and get it per mole. So this would be how I would start the problem. If I started each of these and got it per mole, this would be now the heat capacity per mole. I could then say, okay, what would that mean in terms of increments of R? And it comes out really close to these whole numbers. We've seen how at the particle level, that's our increment. It's in increments of R. So if you got it to this point, then I think it really set up your analysis and it could be a lot stronger. You could then see, well, why is the heat capacity of the metal close to 3R? A discussion here was that we would have 3 translations that would take place. And because it's a solid, there would be potential energy attached with each of those. That's why we see metals with our DeLong-Petit law really being close to a value of 3R. Much of the discussion for the metal, if one did not calculate and consider units of R or increments of R, described the copper as being monatomic. So therefore it did not have rotations present. I get that. But remember, we're talking about it monatomic in the solid. There's a potential energy value as well. So it wasn't the copper atoms all by themselves. It's not gaseous copper. It's copper metal. When we're looking at the H2O, when it's water vapor, gaseous, to make sense of a increment of 4R, well, if I combine my translations, combine rotations, and then I consider it having the potential to do PV work, so let's say under constant pressure, that gets me right to an increment of 4R. Much of the discussion on this, if one did not consider the increments of R, it was in more general terms, and it often included a discussion of the intermolecular forces that would be present. I don't think that that is a key contributor when we're talking about water vapor. I think we're talking about it more as an ideal gas. where we're interested in these features right here: translations, rotations, and the chance to do opportunity to do PV work. The opportunity to do PV work within this set of questions right here, I thought that was a key point when we're looking at our coffee cup calorimeter. The best responses for this one did a good job of describing how when you're using a coffee cup calorimeter, that's an enthalpy change. The system has the potential to do PV work. The transfer of heat that I have within that is at constant pressure. The pressure is 1 atmosphere. It's the opposing atmospheric pressure. And there's the potential to do PV work. Starting the discussion that way led, I thought, to the best responses. The analysis within this next one, this was our consideration of Kirchhoff's law. The stronger explanations here when considering the enthalpy change mentioned the heat capacity, how that was what was affecting the slope. There were some interesting discussions then about what the change in enthalpy would mean. Could the values eventually cross? And I thought the best discussions there went beyond simply, well, look at the slopes of the lines. Yeah, they'll eventually cross, to what that really meant. And when I say what that really meant, there's a lot going on there as far as what does it mean in terms of aspects of bond enthalpy when we're comparing reactants and products, and also the relative magnitude of that with the contribution from the heat capacity. So I found it interesting what you all had to say on that one. Also interesting was our calculation here using provided bond enthalpy data. That one was sort of remarkable. I think we're a class of scientists, not necessarily a class of accountants. I say that because every student that tried this one, you were absolutely having the right plan. You were absolutely setting it up correctly. But in terms of then working it through, counting the actual bonds, getting to the final answer, almost every student had a different answer. No joke within that one. If I looked at the setup, it's like, okay, yeah, I can see what you're doing. I can follow through. This is making sense. Oh, wait a minute. This number is different. This number is different. This number is different. So I really found within that one, I was scoring. I mean, it's a science class. I'm not scoring that question entirely for what an accountant would tell me. I mean, I liked the plan that you had, but there was a lot going on in terms of balancing that, counting the correct number of bonds, just simply doing the arithmetic correctly. So the variety of the answers for that question is really remarkable. Towards the end here, we had two different ones where we're looking at contributions to enthalpy, whether it was the Born-Haber cycle or looking more closely at provided bond enthalpy data. For the Born-Haber cycle, I found there was a lot of variation on really the step of what we were trying to put together that was going to form the ionic compound. I agreed that I would be taking this metal to be +4, and I would say then I had two oxide anions, each -2. I found within this one there were different representations of what we were trying to get to combine. This would be one that I thought was one of the most complete. It was including the stage here of the second electron affinity being unfavorable. This particular one, I think in some ways, we have not done a lot of work with actual chemistry and looking at the periodic table. I know that. We've done a lot with quantum. We've done a lot with these different materials. We've done a lot with aspects of heat, work, thermodynamics. This particular question, I think my 1210 students would do a little better with, just because they've done a lot of more, quote, chemistry. Within this one, I found it's perhaps the case we haven't done as much chemistry, so that idea of simply saying, well, what are we combining, might have been a little bit more challenging. This question at the end here, influencing the strength of bonds, considering aspects to bond enthalpy. Interesting discussion here. My leading three variables I would be looking at were bond order, atomic radius, and the presence of lone pairs. Those are the ones that I mentioned in class, and those would be the ones I would be choosing examples for. But I understand that this could also be bundled in with aspects of electronegativity. especially this concern of atomic radius, lone pairs, and electronegativity, you got to be really careful, I think, with the examples that you're choosing in the case that you're trying to make. Bond order is easy as we're comparing single, double, triple bonds, but these other ones, they get bundled together. My point, let's say we're comparing the bonds in H2 with a carbon-hydrogen bond and a nitrogen-hydrogen bond. If I'm considered these in terms of electronegativity, I don't think it holds up at all. That wouldn't be what I would be using within my comparison. Because if I look at this, the covalent bond in H2 has a greater bond enthalpy than the more polar bond in carbon-hydrogen. Even though carbon-hydrogen does not have any lone pairs. I'm grabbing a typical hydrocarbon there. Carbon usually does not have any lone pairs present. So this would be one where it sure seems like it's countering any trend in electronegativity. Lone pairs don't seem to be involved. But in this case, I think the atomic radius would be the key thing that I'm using within my explanation. If I continue on, it's even more polar with nitrogen-hydrogen, and that's the weakest out of the set right here. How do I begin to explain that one? Because after all, nitrogen is smaller than carbon. I think nitrogen many, many times has a lone pair present. So I think that these average bond enthalpy values, oftentimes the nitrogen atoms that are included in that have lone pairs. That's what I mean when I say it gets more complex. I find an example with electronegativity, you can run into trouble many times. As I look within the set, what I think the best example, if I had to make the case for electronegativity, it might be within this group right here. I think in O2, this is the value for the double bond in O2. I think in S2, that would also be covalent. This would be oftentimes a feature that I would have in S2 very similar to O2, that double bond. So both of those which are quite covalent, if I get a difference in electronegativity like sulfur and oxygen, I see the bond strength going up. And I don't think that that is one where it's a case of the lone pairs are somehow being part of the issue, because I think we inevitably, many, many times in our most common structures here, we still have lone pairs, whether we're talking about in oxygen or in sulfur. So if I had to pick an example or find an example, it's not obvious within this where I don't have these other terms somehow being part of the explanation. This would probably be the best feature. I enjoyed reading your answers within this. There's a lot going on. I come back to in my own explanations, I find those top three, bond order, atomic radius, and the destabilizing effects of lone pairs, oftentimes for me, form the strongest explanations.